How y'all doing tonight? Yeah, enjoying this weather? Cooling off a little bit? I am. Wonderful. You know what I just realized, actually, just yesterday, is that tonight is a very special night for me. It's my 1-year Austin anniversary. Woo! I rolled into town for the first time a year ago, almost to the hour, with my partner, my cat, my dog, my composting worms, and a few suitcases. And we've really enjoyed being in Austin, from everyone at the university and also the city itself. It's really a wonderful place to be. And I'm sorry for you Austin diehards who've been here forever. I'm part of the problem moving to Austin. Anyway, so tonight, what I want to, let you in on is a little secret. And this secret has something to do with dust. And I'm not talking about, the dust that collects in the corner of the room that you occasionally get to once a month, and you might neaten up if you have some guests coming over. But I'm talking about really special intergalactic dust. This dust is a bit more like soot than dust, and it does some very special things to electromagnetic radiation, particularly in the distant universe, which is what I specialize on, is galaxies in the distant universe. Okay, so I want to start off today by showing you guys this image. Who here has seen this one before? Raise your hand, right? Does anyone know what telescope took this image? Hubble. Oh, you guys are experts. So this is the Hubble Ultra Deep Field, which is one of actually the deepest image ever taken of the distant universe by the Hubble Space Telescope, which has now been operating for about 25 years. And this image is very special because almost every pinprick of light in the image is from a distant galaxy. It's not a star. And so this has been a very important image to teach us about how galaxies in the most distant universe came about, formed and evolved to, all the way to the present day. Because the further we look, the older those galaxies are. But this isn't the entire story. This is just the tip of the iceberg. I'm going to show you another image here, and you tell me if you've seen it. Anyone seen that? Okay, astronomers don't count. So this image is really similar to the previous image I showed you of the Hubble Ultra Deep Field. It's another snapshot at the distant universe, but it's taken at a very different wavelength of light. So if I remind you about the electromagnetic spectrum, it goes from very energetic light rays from the gamma rays to very low energy light at radio wavelengths. And the visible spectrum, which is where human beings kind of live their entire experience, is right in the middle here. So we see the visible light, we radiate near-infrared light. It's all in that tiny little range. So it's not really surprising that the Hubble Space Telescope operates in this wavelength regime. This is where our technology has really led the way in astronomy because we know it best. But the image in the background here is taken out at what we call submillimeter wavelengths, or wavelengths roughly 1,000 times what we can see in visible light. And so this is where the interesting story of dust kind of comes alive. Okay, but before I tell you more about that image, I want to take a step back and talk about galactic ingredients. So what makes up a galaxy, do you think? Just, shout it out. Dark matter, stars, planets, dust. Good answer. Yeah. Okay, so let me show you what my list looks like. Stars, that's a pretty important ingredient. That's what makes it shine. Dust, of course, because that's what this talk is about. Gas, there's a lot of gas, although it doesn't look like that. Dark matter, of course. Didn't know how to draw dark matter, so. Planets, they're cute. There are a lot of them. We know that, whatever. Black holes, again, had no idea how to draw that, so Little cereal box of black holes right there. So you guys are leaving out a pretty important ingredient. Am I right? Any guesses?
Dark energy?
Oh, dark energy. Well, no, good. I'm not actually being serious here. Pokemon, rare Pokemon. Anyone? Catch 'em all, right? Okay, but in all seriousness, I'm going to leave out that exciting stuff over on the edge there, and talk about what makes this talk exciting. These pretty fundamental building blocks on the left: stars, dust, and gas. So what do stars, dust, and gas do to one another in galaxies? Okay, so if we start off with gas, because that's what we had after the Big Bang. We had just a lot of gas. We didn't have stars directly from the Big Bang. Mostly hydrogen gas. If we have a way of compressing that gas into its molecular form, it becomes very efficient at forming stars. So actually, from the gas, we get stars. So gas fuels star formation. It's not unlike the gas that fuel our cars and other things. Okay, but what happens when stars kind of trickle off and die? So stars will live their normal lifetime, and in the process of them dying, they actually do this interesting thing where they produce a lot of dust. And it doesn't take a lot, well, not a lot of dust compared to the mass of everything else in the stars, but even just a tiny little bit of dust they produce that is ejected into the interstellar medium, kind of out there in space, and then it does some interesting stuff. Dust, in turn, then obscures starlight from new stars. Okay, so what actually happens is when you have a bunch of stars and they're surrounded by some dust, or dust is between us and those stars, you get the visible light from the stars, which is where their spectrum peaks. Most of the energy is coming out at visible wavelengths. But if it runs into the dust on the way, what happens is that dust is heated by that light, and the energy is re-radiated at submillimeter wavelengths. So this is actually submillimeter light that we see coming from dust. Okay, so I'm going to get a little bit technical on you just for one slide and show you a spectral energy distribution of a typical galaxy, not unlike our Milky Way. It's pretty average. And the key take-home point with this squiggly line you see on this plot here, so this is energy output versus wavelength, is these two regimes using the same color scheme from the previous slide. The blue peak here represents emission from starlight, so that's visible light. And the orange peak is what we see from dust emission in the submillimeter. So in normal galaxies, that will be roughly balanced. You'll see the same energy output total in those two regimes. But what's kind of interesting, which I think about quite a bit, are galaxies that don't have that balance equal. And this type of galaxy on the right here are called ultraluminous infrared galaxies. And they're noted for having this balance completely out of whack. Most of their energy, over 99% of it, is coming out in submillimeter wavelengths. So it's mostly dust emission. It's not that starlight. So what's going on in these ultraluminous infrared galaxies? So I'm going to show you a few pictures of ultraluminous infrared galaxies that we can see really well because they're fairly close by in the universe. Do you guys notice anything special about these galaxies? They all have dust in them. That is a true statement. Okay, so they're not spiral galaxies, are they? Or ellipticals? No. So what's happening here is that they are all galaxy mergers, aren't they? Yeah, that's kind of wild. So they're some of the most interesting places to be in the universe, I'm sure. I'm told. I'm biased, but they're pretty cool. Yeah, so galaxy mergers have something to do with dust, right? But why is that? What does dust actually have to do with galaxy mergers? Okay, so we think we've figured the story out a little bit, at least. We have this scenario in my field where we think, we can produce an ultraluminous infrared galaxy pretty efficiently if we just crash two Milky Way type galaxies together. Not a big deal, right? Okay, so you take two normal disk galaxies, you crash them together, the gas inside of those galaxies collides, collapses into molecular clouds, and you get a lot of star formation. But this star formation is pretty short-lived. It only lasts about 100 million years, super short, right? And then what happens to the two galaxies which collided, there are only one galaxy now, and that actually leads to the formation of elliptical type galaxies. So we think most elliptical type galaxies formed in these galaxy mergers and went through a stage where they were an ultraluminous infrared galaxy, or very dusty. But I'm interested in that dusty phase. That's when the star formation rate peaks. And since you have a lot of star formation, if you have a lot of dust, it does a very efficient job at obscuring the starlight. I should also point out that if you put the merger on the star formation rate scale, the star formation rate in these buddies can be 100 to 1,000 times the star formation rate in normal type galaxies. So if you're counting up, how fast stars are forming in the universe, you better include these mergers. Okay, so back to this image. What's this conspiracy all about again? It's not really a conspiracy, I guess. But so if we look, I'm going to show you now the first kind of version of this millimeter deep field next to a pretty well-known version of Hubble Deep Field North, which is an older version of the Hubble Ultra Deep Field. I bet you guys have seen that image on the right before, the kind of staircase. But the image on the left, I bet you haven't seen. It's the same image to scale. So those blobs and wiggles kind of correspond to things that sit in that Hubble Deep Field. But what's remarkable about the image on the left is knowing what we know about galaxy mergers and dusty galaxies in the nearby universe. There shouldn't have been a single detection in that image. It should have just been green wiggles. But everything that you see that's purple constitutes a real galaxy detection. So this means that submillimeter galaxies, dusty galaxies, actually make up a significant proportion of the total star formation in the distant universe. Just to show you that quantitatively, this is a pretty important plot to me and my research and to galaxy evolution as a whole. It's measuring the total star formation rate of the universe over cosmic time. So the x-axis is showing you just time. Today is on the left, and the Big Bang is on the right. And the y-axis is the density of star formation in the universe. So some star formation per unit volume, kind of integrating over all galaxies that are out there. So in today's universe, Milky Way type galaxies dominate. Most stars are forming in those. But in the distant universe, beyond like 8 to 9 billion years ago, extreme dusty ultraluminous galaxies, these ULIRGs, dominate. So if we want to understand how galaxies were evolving and forming in that early universe, we better understand these dusty ULIRGs. So what do they actually look like? These are some snapshots of ULIRGs in the distant universe. You'll notice they're not quite as pretty as the galaxy mergers I showed you earlier. That's because they're really far away, and they're really dusty again. So, most of their light is coming out at long wavelengths. This is kind of a melange of different wave bands that you see here. But one thing you'll notice is that it's not so easy to tell whether or not these are galaxy mergers or not. And this is a really active area of research in my field. We don't know what ULIRGs in the early universe were doing. Were they galaxy mergers? That's kind of the default assumption. But they could have been built by different mechanisms, because we know mergers are kind of rare, so maybe because these are not rare in the early universe, they formed via some cold gas accretion. So this is a hotly contested issue. But thankfully, we have a brand new toy on the horizon. Well, not on the horizon. We've been playing with it for a few years, but now it's really getting going in full gear. This is the AoTATX Large Millimeter Array, or ALMA. It's like our Hubble Space Telescope, or rather, HST is the ALMA of the optical, we like to say. ALMA is a fantastic, groundbreaking telescope that is really changing the way we do astronomy. It's giving us some of the most fantastic views of the universe from the dust and gas perspective. For example, this is TW Hydra, a planetary disk in formation. You see the gaps, the rings are planets that are sweeping up gas and dust in where a young planet is forming. And this beauty here, this is a galaxy called SDP 81, which is very distant. It's a ULIRG, but it happens to be gravitationally lensed. So that's why it looks like a ring. Okay, so just to wrap up here, I want to play a little game. It's where you get to guess which galaxy is the ULIRG. So this is based off of recent ALMA data that I've just obtained, and I compare it to HST data. So the blue is HST, and I'll show you orange is ALMA. So galaxy 1, 2, or 3, which one do you think is the ULIRG? 2, 3. Okay. 2s win. Good job. Okay, here's one more. 1, 2, or 3? 3. I maybe hear 3 the most. Oh, we're all losers. This is welcome to my life. I tried this game. I thought it was 1. No go. No go. Whoops. And one last one. 1, 2, or 3? 1, 2. Oh, everyone. Yeah, it's a confusing game. Right? Am I right? Okay. 1 and 2s get it. And then there's a random third one. Didn't guess that. So life is hard in this millimeter world. So just a last slide here. I wanted to show you this beautiful image because it's one of my favorite galaxies. It's Cen A. Zooming in on a portion that we can actually see, the dust lane around the middle here. And I just wanted to highlight, in case you forgot, what makes this image so beautiful? Dust. Thank you.
So we'll have a few minutes for questions. Let's go up first. Say that again. When did ALMA come online for those trivia goers?
Man, can I answer that? I mean, that's a trivia question.
It was on the slide though, wasn't it?
It was on the slide. It was okay. Well, okay.
We have some diehard trivia people here.
2011. Cheater.
You, sir.
You said that stars formed during galaxy mergers have short lifetimes. Why is that?
No, so what happens
Can you repeat the question? I'm sorry.
Yeah, sure. So do stars in galaxy mergers have short lifetimes, and why is that? So what happens during a galaxy merger is you just get a bunch of stars forming. Those individuals, so the episode of star formation, so how quickly you are forming stars is short-lived, but the stars will have various lifetimes. They'll be very long-lived if they're low mass and short-lived if they're high mass. So that doesn't change. It's just how quickly you're forming the stars. Right here?
If there are more than 2 galaxies in the galaxy merger, are the period of star forming more intense?
Yeah, that's a great question. So the question was, if you have more than 2 galaxies in a galaxy merger, is the episode of star formation even more intense? So that's going to be pretty rare, just because colliding galaxies are overall pretty rare. But if that were to happen hypothetically, yes, it would be even more intense. So we see examples of very intense merging starbursts, and that's usually caused when you have very massive galaxies. So if you involve more mass and more gas, you'll get a more intense burst.
Question over there.
How do you think the potential advent of neutrino astronomy is going to affect our ability to observe this?
How will the advent of neutrino astronomy affect our ability to see ULIRGs? It won't. We see them pretty well, and it's just, this is a regime where we really need these submillimeter facilities, and it's just a totally different regime.
Right here.
Do we understand the trigger for a galaxy collision?
Oh, like what causes 2 galaxies to collide? Well, it's gravity. Mostly, yeah. So basically, on the largest scales, gravity is dominating the game, and if you have the collapse of large-scale structure, that large-scale structure will contain galaxies, and sometimes they'll collide. Great. No, we don't. By the way, the Milky Way does not, and we're going to collide.
Okay, one last question right here.
What is dust made of? That's a great question. So it's mostly like soot, like carbon, molecules, but it can be all grains of all different sizes. Dust, on the technical side of things, can be a complex definition and kind of cover many different regimes that way. But as long as it absorbs visible light efficiently and then re-radiates it at longer wavelengths, we call it dust.
Okay, great. Well, let's give Dr. Dustbuster another hand.